Greetings, everybody. Welcome. And my job here is to set the stage with some hydrogen basics to make sure that everybody is on the same page for the rock star presenters that are yet to come. So that's my job. So as soon as the slides come up, we'll get at it. All right.
There we go.
Excellent. Okay, so next slide, please. And so what is hydrogen anyway? You know, it is the first element on the periodic table, and it's the smallest one we have. On the left, you can see that hydrogen doesn't hang out as a single atom, but it hangs out as a molecule made of two atoms of hydrogen bonded together into H2. That hydrogen bond is critical because that is where the energy is stored. Next. There is a lot of hydrogen in the universe. Next there, Nick. About 73% of all of the atoms, about 73% of all the atoms in the universe are hydrogen, and it is the fuel of the universe. Next. However, there's very little hydrogen roaming around by itself on Earth. Most of what we have is tied up in the ocean water. So we have to actually use energy to make it. And hydrogen is therefore not an energy source, it's an energy carrier. Or it can be called a fuel as well. Next. So take some time to take a look at the hydrocarbon chemical structures. The first three molecules represent coal, oil, and natural gas. And you can see there's lots of carbon atoms in there. And when we burn these for energy, CO2 gets pooped off into the atmosphere. But where does the energy actually come from? Most of the energy is held in the hydrogen bonds, hydrogen to carbon bonds. And when we break those bonds by burning hydrocarbons, we release the energy for our use, right? So why hydrogen? Well, shown with a red arrow, there are no carbons at all in hydrogen. So when we break the hydrogen bond for energy, no CO2 results, and that only water, and that's why hydrogen. Next. So the world is moving away from burning hydrocarbons because of climate change and the resulting weather weirding. This pie chart shows us the effects of various greenhouse gases currently overheating our atmosphere. Look at the biggest blue pie slice on the right. The lion's share of atmospheric overheating comes from excess CO2 emissions from burning fossil fuels for energy. 62% on a worldwide basis, in fact. Only 20% of those emissions are actually emitted by oil companies, though, you know, when they make the fuels for us. The other 80% comes out of our own tailpipes and our own chimneys. If we could use hydrogen for our energy needs, our only emission would be water. Next. So why does CO2 warm up the atmosphere anyway? Well, our planet has an ancient natural blanket of heat trapping gases in the atmosphere, which is dominantly CO2. And this natural blanket keeps the Earth about 30 degrees Celsius warmer than it would be otherwise. And that's a good thing, right? It's natural. And it works just like a blanket that traps your body heat on a cold night. So what the heck's the problem anyway? Next. Well, the problem is by digging up and burning coal and oil and natural gas, which release large quantities of CO2, we are wrapping an extra blanket of heat trapping gases around the planet. And just like you would if your grandma snuck into your room at night and put an extra down comforter over you, you'd wake up sweating too. Next. So we're trying to keep our planet under 2 degrees C of extra atmospheric heating, which doesn't sound like much because we think, you know, it's just about air temperature outside. No big deal, right? But that's not the way it works. That's weather. That's not climate. Climate is measured as an average of the weather over 20 to 30 years, and it works more like a fever in your body. If your body ran an extra, like a 2 degrees chronic fever of say 39 Celsius, or for us older folks, 102 Fahrenheit, then you wouldn't be operating very well either. Next. So what can we use hydrogen for? There's a lot of things that electricity does really well, but things it just doesn't do very well, but hydrogen does. So the biggies are highlighted in yellow on the slide, and they include heavy long distance transport like freight trucks, buses, trains, and shipping, and eventually planes. Industrial heat like for steel and cement making. Seasonal large scale electrical power storage. Hydrogen is the only thing we've got. Space and water heating, and feedstock for fertilizer production and other chemistries. Next. The world is getting onto this now, and some countries are moving faster than others. Over 25 countries in the world have already published their hydrogen strategy. And in December, Canada released our federal hydrogen strategy, 141 pages, which was very well received, I might say. David Lazell, who you will hear from next, had a lot to do with that document. Next. So how do we make hydrogen? Like, there is a color taxonomy which speaks to the process for making it. And this chart shows you how many kilograms of CO2 is produced for every kilogram of hydrogen that is made. Now, I want you to notice a couple of things. There are ranges of carbon footprint for each of these types of hydrogen production, depending on the circumstances. So you can see that what really matters is not so much the color of the hydrogen, but it's the actual carbon footprint. Anything less than 5 kilograms of CO2 is considered to be low carbon hydrogen by the European Union. Still, I think it's useful to know what the colors mean. So let's get into that. Generally, the 3 lowest carbon footprint hydrogen processes are pink, which uses nuclear electricity for electrolysis, which splits water into hydrogen and oxygen, and also green, which uses renewable electricity from hydro, wind, solar, tidal, wave, geothermal, to do the same thing. And also blue, which uses natural gas and water to make hydrogen and CO2, on the condition that that CO2 is sequestered permanently in the ground. They are all considered low carbon hydrogen by the EU's definition. So that's the first 3. Now let's look at the middle 3, which also have the possibility to produce low carbon hydrogen by electrolysis, but they also can be higher carbon, as they have much more carbon footprint variability depending on the circumstances. So these are turquoise. This is where we heat up natural gas in a certain way and make hydrogen and or not none, but less. White is byproduct hydrogen from industrial processes like chloralkali plants, which make chlorine and sodium hydroxide. And yellow, which is about using grid electricity for electrolysis, but the grids can have highly variable footprints of carbon footprints, as you can see from the length of the yellow bar. The last 2 processes have the highest carbon footprints in their processes because they both use hydrocarbon feedstocks, and they both poop the resulting CO2 off into the atmosphere. Gray uses methane and water, and brown uses coal. So today, about 95% of the world's hydrogen is produced by gray and brown processes today. About 3% is blue, about 2% is green. So we really have a lot, and I mean a lot, of room for improvement. Next. So turning to the Canadian domestic hydrogen market now, we estimate by 2050, Canada alone will need to produce about 7 times the amount of hydrogen that we do today. This means going from 8,000 tons of hydrogen a day to 58,000 tons a day. Now, that's a big domestic market. How the heck are we going to get that done? Well, here in Canada, we are absolutely blessed with resource endowments to make hydrogen. Green dots are for the hydro dam powered green hydrogen in Quebec, Manitoba, and to some extent BC. That is to say, using renewable hydroelectricity to split water into hydrogen and oxygen. The big blue dots on the map represent blue hydrogen in Alberta, BC, and Saskatchewan. And this is where we have natural gas resources to actually make blue hydrogen. That is to say, heating up natural gas with a bit of nickel catalyst in there. And out comes pure CO2 emissions needed for sequestration back into the earth and hydrogen. The pink dots are for nuclear electricity used for electrolysis of water to make pink hydrogen. Nuclear is actually Ontario's big expertise, but also New Brunswick and Quebec as well. Next. So what's happening internationally? Well, this chart plots hydrogen production potential against domestic hydrogen consumption. Where the country wants to be is in the upper left quadrant. This is where their ability to produce hydrogen outstrips their domestic consumption, and thereby they've got extra to export. Countries on the bottom right consume more hydrogen than they can possibly make, so they are the importers. Now, we are starting to see an international movement of hydrogen along the green arrow from the countries with enough hydrogen to countries without. Note that Canada, highlighted in yellow here, is in the exporter category. We think we should be able to export at least as much as Canada's domestic hydrogen requirement. Next. So what do we have going on in Alberta so far? Well, this is the Shell Quest project, which sequesters 1 million tons, that's to say a megaton of CO2 every year in the earth, and has been doing that for the last 5 years. It's just north of Fort Saskatchewan in Alberta. Next. The industrial heartland. Next one, Nick. Well, the Industrial Heartland Working Group have set the stage to be Canada's first hydrogen hub northeast of Edmonton, and is working with the Transition Accelerator. And Dave Lazell will say more about that right after this presentation is done. Next. So the AZATech project is, and that's out of the University of Calgary, the Caesar Group, is building 2 big hydrogen fuel cell powered Class 8 freight trucks for test runs between Calgary and Edmonton starting this fall. Now I want you to notice the range of companies in this collaboration. Like, collaboration is the only way we're going to get this hydrogen economy thing done, because of the chicken and egg nature of supply and demand when it comes to hydrogen. Hydra is another one of our corporate gems involved in hydrogen trucking, as you will be hearing from the President Bader today. So that's pretty lucky. Next. Alberta also has the Alberta Carbon Trunk Line, pictured here in orange, and it's the longest CO2 pipeline in the world. They actually pay $20 a ton for CO2 and then inject it into the Clive Pool near Red Deer to produce another 1 billion barrels of oil that would not otherwise be recoverable, and sequestering some of the CO2 in that process. Next. ATCO is working on blending hydrogen into natural gas pipelines in the city of Fort Saskatchewan.
Maggie, your audio just went out.
My audio just went out. Why? Can you hear me? Am I back? Oh, I just got your internet connection is unstable sign. Can you hear me now?
Yeah, loud and clear now.
Okay. Yeah, loud and clear now. Okay. So, so let's just go back to, yeah, let's just do this. So if you didn't hear me, I just wanted to say that ATCO is mixing 5% hydrogen into their hydrogen, into the natural gas lines. And they hope to ramp that up to about 20%. So now we'll go next. Oh, and so bottom line is, we know, Alberta, we have a good start, but we have a lot of work to do collectively. some jobs to generate, and some carbon to mitigate. But if we get this post-carbon energy transition stuff right, the future generations will look back at us and laugh, saying, you know, I can't believe our ancestors actually burned this valuable stuff. You know, it's good for so many other things. You're really in for a treat today, hearing from some of the movers and shakers here in Canada. And that is, they're the people that are actually making this happen. So finally, thank you for your kind attention. Here are my coordinates. I was going to say feel free to take a screen capture, but it's too late now. And reach out if you have any further questions and queries down the line. I will actually put my coordinates in the chat box, so you can grab them there. Thank you, everybody. Hope that set the stage for you.
Perfect. Thank you, Maggie. So now we'll have a short question period. And I see one of the top questions right now is, can you read the question, Maggie? So I'm surprised green. Yeah, I'm surprised green renewable.
I'm surprised green renewable electrolysis has some carbon emission from production. What is the source of the CO2 by producing green hydrogen? So the carbon footprint of a thing is best looked at on a life cycle basis. So on a life cycle basis, and that's what that chart I showed you was, a life cycle basis. So it includes building the equipment. You know, it includes moving the equipment onto site. It also includes for things like if you're using hydro for your power to make that green hydrogen. Hydro dams have a dirty little secret, you know, they emit methane and CO2. In northern climates, they emit more CO2 than methane, and southern ones, you know, closer to the equator, more methane than CO2, but still that's included in the carbon footprint. So I hope that answers your question. Next question, does the amount of carbon in coal, oil, and gas correspond to the amount of carbon dioxide created when those fuels are burned? So yeah, absolutely. The more carbon is in coal. Coal is higher carbon, higher proportion of carbon with respect to the hydrogen in it. Oil is next and natural gas is next. So that's absolutely correct. What does the color refer to? Just the name for a type of fuel? Not exactly. The color is more about how each of those you know, how hydrogen is produced by those different methods, right? So if you're using natural gas and water together and heating it up in a steam methane reformer, that's called blue. When you sequester the CO2 in the ground, that's called blue hydrogen, right? So the different hydrogens have different names depending on how that hydrogen is made. Next. Do green and blue hydrogen have any waste products created during the process of using the fuel, like nuclear waste created from nuclear energy? So green hydrogen, not so much. Blue hydrogen, yeah, there is a waste, but we sequester 90% of that in the ground. It's the CO2 that goes into carbon into at least 2 kilometers deep in the ground and in the earth. And so that's a waste product, but we know how to deal with it. And that actually makes blue hydrogen a very low carbon footprint type of hydrogen. Nuclear waste, absolutely, is a waste from making the power for paint. And at the same time, nuclear waste isn't as big a deal as a lot of other kinds of waste. It's very compact, it's very small, we know how to deal with it. And we have different kinds of nuclear reactors coming online now that actually can burn that nuclear waste and take more energy out of it. So I'm actually a fan of nuclear. Let's see, what else we got here? Does the CO2 pipeline work by pushing the oil through faster than it would come out by itself, or in place of using another type of fuel to push out the oil. Okay, so we're talking, I'm guessing here, but I think we're talking about the Clive pool. And basically, when you put CO2 into the reservoir with the oil, the CO2 dissolves into the oil, reduces the viscosity so that the more oil can be pumped out. Like it takes it from being quite thick to a lot thinner, and then we can produce it a lot easier. So I hope that answers your question.
Thank you, Maggie.